amines, which is good, and then we'll do some practice. Okay, so where we left off at was talking about diazonium ions, and I explained to you how we make the nitrosodium ion by making nitrous acid in situ. So we went over that in detail. And then I said, okay, well, if you have an alkyl diazonium salt, you can see I have it highlighted at the top. They're extremely unstable. They decompose. They give you a whole bunch of products. They're explosive. So that's not good. But if you have an aryl diazonium salt, it's more stable and it's synthetically versatile. And that's what we're going to talk about right now. This is an aryl diazonium ion right here. So if you have an aromatic ring with a diazonium ion on it, you can do all kinds of interesting chemistry. So let me show you some of that. And the first kind of reaction that we're going to look at is called the Sandmaire reaction, or Sandmaire reactions because there's a few of them. It's a reaction of an aryl diazonium with a copper salt to install a halogen or a cyano group. And I should point out it's a copper 1 salt. So we have copper 1 bromide reacting with an aryl diazonium that installs a bromine. Copper 1 chloride reacting with the diazonium gives you chlorine. Copper 1 iodide gives you an iodine when it's reacting with the diazonium. And copper 1 cyanide gives you a nitrile when reacted with a diazonium salt. So copper 1 bromide, copper 1 chloride, copper 1 iodide, and copper 1 cyanide can give us a aryl bromide, chloride, iodide, or cyanide. All of those. Now, you might be wondering, what about iodine, or what about fluorine? That's something that we're going to talk about in a little bit later. But right now, these are the Sandmaire reactions. And something that's really cool about these is if you think about, what are the possibilities? I mean, if you have benzonitrile, for example, I'll just try to scribble it in here. If you treat that with aqueous acid and heat that up, that hydrolyzes to give you benzoic acid, right? So that's kind of a cool thing, another way to make benzoic acid. Anyhow, let's see here. It says, overall, the Sandmaire reaction is part of a multi-step sequence to install a carboxyl group on a benzene ring. So this is what I was just getting at. All right, let's say you have this molecule here. This is called cumene or isopropyl benzene. Cumene is the common name. If you take cumene, you nitrate it in the first step. So you have the nitro. Then you reduce it with iron and aqueous acid, treat it with sodium hydroxide. That's going to give you the amine. Then you diazotize with sodium nitrite and HCl, and that gives you the aryl diazonium salt. Then you do the Sandmaire reaction. So this is a Sandmaire reaction with cuprous cyanide or copper 1 cyanide, either way. That gives you the nitrile, and then that's hydrolyzed to a carboxylic acid. So a really cool way to make a carboxylic acid through or via a Sandmaire reaction. Now there are some other neat reactions I'm going to show you with aryl diazonium ions. This one here is called the Shemen reaction. So the installation of the fluorine, let me see my spelling here. No, that's not right. If it's, let's see. Shemen, yeah. This is called the Shemen reaction, where you take the aryl diazonium and you treat it with fluoroboric acid. So this is called fluoroboric acid, and that can give you an aryl fluoride. So that's not considered a Sandmaire reaction. It's something different with fluoroboric acid. Also, you can make a phenol if you just treat your aryl diazonium ion with water and heat that up. So that gives you a phenol. And what's cool about that is there's not many ways to make a phenol. We don't have a ton of ways to make a phenol. And there's one more reaction I want to show you with an aryl diazonium, and that is just if you want to remove the diazonium ion, you can replace it with a hydrogen atom using hypophosphorus acid. So if you have H3PO4, that's phosphoric acid. If you have H3PO3, that's phosphorus acid. And if you have H3PO2, that's hypophosphorus acid. So this is hypophosphorus acid. Just a little review of acid nomenclature there. So hypophosphorus acid replaces the diazonium ion with a proton. And that's kind of cool because if you need an amino group on a ring temporarily, then it can be removed. So let's say you wanted to make this compound here, if you wanted to make 1,3,5-tribromobenzene, well, we know that we can make that from aniline. So first you would make aniline and then you brominate it, and it just brominates everywhere. And then you can just get rid of this by doing the diazotization, followed by treatment with hypophosphorus acid, and that just converts the diazonium ion into a hydrogen, and you're done, my friend. Now, it might not be a reaction that we do a lot, but it would, it's useful because this molecule here, sorry, where's my pen? This, thinking about making this molecule, this is actually difficult to make otherwise. Because if you were to put one bromine on, well, bromine is an ortho and para director. It's not a meta director, and it's also deactivating. So I really can't think of another way to make this molecule other than to use this strategy. The last section, or the last part of the diazonium salts, it deals with what's called Azo Coupling. And I can't remember which chapter it was. It might have been chapter 18. The introduction to the chapter had a little section about the dyes that are found in Fruit Loops. I'm not kidding. If you go to the beginning of, I think it's chapter 18, there's a whole blurb in there about the dyes that are found in Fruit Loops. And the dyes that are found in Fruit Loops are actually made, or Fruit Loops or Fruity Pebbles, I don't know, anyhow. They're made via what's called an Azo Coupling, and that is made from, or through, or with a diazonium ion. So it says diazonium ions, diazonium salts also serve as electrophiles and can be attacked by an aromatic ring if it's activated, and we call that Azo Coupling. So Azo Coupling, and this goes right back to your chapter 18 days. If you take an aromatic ring that has an electron donating group on it, so some kind of activator, right, that can act as a nucleophile towards the diazonium ion, and it gives you a sigma complex. Seen that before, haven't you? Look, we draw all the different resonance structures of the sigma complex, and then what happens is the chloride from the beginning, from the diazonium salt, ends up removing a proton to restore the aromatic ring, and you end up with this diazo compound. So we call this azo coupling, and we call this a diazo compound. All right, when we have two nitrogens in between our two aromatic rings, and the two nitrogens have a double bond in between them, and this functional group is very commonly found in dyes. It says azo coupling is used to make azo dyes. Oh yeah, it is in chapter 18. And these azo compounds, they're super highly conjugated, and therefore they have these really bright and brilliant colors. I just noticed in my notes here, I wrote not Fruit Loops, Fruity Pebbles. So I guess I'm right. Anyhow, so you can go back and read that if you want. But if you're wondering, where do they get these really neat colors from? They come from azo dyes. And if you look at the ingredients on things like Fruity Pebbles, it'll say, sometimes dye number this or dye number that. Well, that's what they're referring to, are these kind of dyes. Anyhow, so what they do is they vary the substitution on the aromatic rings, and that changes the color of the dye. You get these really vibrant colors, which is kind of neat. With all of that in mind, let's see if we can do some synthesis problems. I'm going to have to switch over to a blank document because I don't have a lot of space on here. But let's see if we can tackle these three, and then maybe we'll take a break and we can try some more after that. We'll see here. So let me switch over to a blank document. So this is 22.26 from your textbook. Just bear with me here. So 22.26. The first question was taking nitrobenzene. So if we want to take nitrobenzene and we want to convert that to meta-dibromobenzene, this here, like that. How would we do that? Well, you got to remember that both of these are ortho-para-directing, right? Those are both ortho-para-directing. So we can't just install a bromine and then install a second bromine. However, we have a meta director here, so we could add a bromine to nitrobenzene, and that would go into the meta position, right? We could just take that and treat it with bromine, Br2, and iron 3 bromide, and that would put a bromine in the right position, right? We could put a bromine here. So my question to my students is there something that we've looked at today? You know, it might be a couple of steps, but how we could convert a nitro group to a bromine? Can anybody tell me the name reaction that you would use to do that? Take a nitro and convert it to a bromine. There's a name reaction that we looked at today. Because we know that we can take that nitro and we can convert that to an amine via reduction. And then we can take the amino group and we can do a diazotization to make a diazonium salt. And then we can do a Sandmaire with copper 1 bromide. So let's try that. So if you're not following me, I'll walk you through it here. First, what we would do is we would reduce this to an amine. So we could use iron or zinc. Let's just use iron, and I don't know, you can put HCl or you could put aqueous acid. Either one is totally fine. And that will give you the amine. So we have our bromine here. We have our amino group. Now we can diazotize it. So we will use sodium nitrite in HCl, and that's going to give us the diazonium salt. So that will look like this. We have the bromine here. We have our nitrogen like this. Oops. Like that. And then we're going to do the Sandmaire reaction with copper 1 bromide, and that will install the bromine there. So this is the Sandmaire reaction. Sandmaire. All right. Any questions about that one? Okay. If you have one, don't hesitate to interrupt me. Let's try another one. I thought this one was kind of interesting. So this is 22.26. 22.26 C. We want to take benzene. So benzene like this, and then we want to put in a propyl group, and we want to make a phenol too. And the problem, that you see right away is both of these are ortho-para-directors, right? This is ortho-para-directing, this is ortho-para-directing, and they're meta to each other, but we know that we could make the phenol from the diazonium ion, right? Because we know that if we take the diazonium ion and we just treat it with water, that will give us the phenol. So we could make this from a nitro. Okay, of course we'd have to reduce it and everything and diazotize it. And we also saw that when we learned about Friedel-Crafts, we can't use, you can't use propyl chloride and aluminum chloride. That doesn't work, right? Because this will rearrange. You'd have to use propionyl chloride, right? You'd have to use the acid chloride because that's a meta director. So now you've got two meta directors that you want to install. You want to install, oops, where's my pen? You want to install, this this ketone over here, and then you also want to install the nitro. Well, which one should you install first? Should you do the Friedel-Crafts chemistry first or do the nitration first? Well, the answer is you'd want to do the Friedel-Crafts first because you can't do Friedel-Crafts on a ring that's really deactivated. If you install the nitro first, the ring is way too deactivated and the Friedel-Crafts will not work. And therefore, we're going to have to do this reaction first. We're going to have to make that ketone first. So let's do that. Let me just scribble some of this out here. We'll just erase all that. Okay, so let's see. Let's start over here. We're going to have to take our benzene and we're going to do our Friedel-Crafts acylation. So that's going to need propionyl chloride and aluminum chloride. And that's going to put our acyl group on our aromatic ring like this. And that is a meta director. So now we can do the nitration. We can put that nitro right where we want it. Nitric acid and sulfuric acid. That gives us something that looks like this. There's our acyl group. There's our nitro group. So now we need to reduce the carbonyl. And I don't remember if we discussed this or not in the aldehydes and ketones chapter, but if you do a Clemency reduction, which is, you know, the zinc mercury amalgam, remember that? You put zinc and then you put the mercury like that and HCl, and then you heat that up. So this, oops, my H is kind of ugly. There we go, HCl and heat. This is the Clemency reduction. So Clemency reduction, okay? If you do a Clemency reduction, which is going to remove the carbonyl, since you have it in HCl and zinc and you're heating it, it's going to reduce the nitro simultaneously. So you're going to reduce both of those, right? Because we know that you can reduce a nitro with HCl and zinc. So you would actually end up with, you know, kind of killing two birds with one stone. And you end up, son of a gun, those double bonds are horrendous. There we go. That's a little better. So we end up with our propyl group over here. We have our amino group here. So there we go, our Clemency reduction. And now we want to take this and convert it into the phenol. So the first step is going to be diazotization. I forgot a step here, I just realized, because if you were to do this in HCl, you'd actually end up with NH3+. You'd actually end up with the aniline ion. Therefore, we're going to have to treat this with sodium hydroxide in the second step. Anyhow, next we diazotize, so sodium nitrite and HCl, and that gives us the aryl diazonium ion. This, like that. 1, 2, 3. And the next step is going to be to convert the diazonium ion into the phenol. And if you remember, we saw how to do that. It was just by using water and heat. So let me just move down here. Kind of running out of space here. I'll put water, and then we heat that up like this. And that gives us this compound. I'll just write it in a different orientation now. So 1, 2, 3. And then we have the phenol right there. And there's our product. So Sandmaire chemistry, super useful chemistry. The only little kind of aside in this one is that we did two reactions at once, right? You burned off the carbonyl and reduced the nitro when you do the Clemency reduction. If you broke that up into two steps, that doesn't matter. That's totally acceptable. I'm just saying that it will work to do both of them at the same time. Let's see here. Let's try another one that involves, let's try another one that we could use a Sandmaire. So this is in the same question. This is 22.26C. And for this one, we're going to take benzene, starting with benzene, and then we're going to convert that to a para-substituted compound. So we've got a tert-butyl group over here, and we've got our carboxylic acid over here. Well, there's probably a couple of ways you could do this. We've learned a few ways to make carboxylic acids. But let's try to use our Sandmaire chemistry since we've already been working on it. Let's see here. Well, if we were going to use Sandmaire chemistry to do this, you know, we'd have to have this as our intermediate because the Sandmaire chemistry allows us to install a nitrile, and then all you'd have to do is, you know, heat that with aqueous acid, and that gets hydrolyzed to the carboxyl group. So then, you know, this is going to come from the nitro, right? We're going to need to have the tert-butyl group and the nitro. So which one do we install? Do we install the nitro or the tert-butyl? Can anybody answer that question?
Tert-butyl?
Absolutely, right? We definitely want to do the the Friedel-Crafts first, right, Lindsay? Because if you install a nitro, Friedel-Crafts isn't going to work. It's too deactivating, so I agree with you 100%. Let's start by putting that tert-butyl group in. Let's see here. What we're going to do is we're going to take this and we're going to treat it with tert-butyl chloride, aluminum chloride, and that's going to put that tert-butyl group in here like this. There we go. There's our tert-butyl group. Next, we're going to do our nitration, which is definitely going to go in the para position. That tert-butyl group is so gigantic. It's going to go right where we want it. Like this. So we've got our tert-butyl group. We've got our nitro. Now we're going to reduce the nitro. Just use some iron and aqueous acid. Okay. You could put HCl. You could put zinc. They all work. Like this. There we go. So we have our amino group in there. Now we're going to do the diazotization. So we're going to use sodium nitrite and HCl. And that gives us this. So now we've got the diazonium salt. Now the world is our oyster. Well, at least we can do some cool reactions. So next, now that we've got the diazonium, we're going to use copper 1 cyanide or cuprous cyanide if you want to use the old way of naming it, which probably nobody does. It's old and it's, yeah, some people don't even teach it anymore. And next, we're just going to hydrolyze that to the acid. So we use H3O plus, and acid, and we heat that up. And that gives us the carboxyl group like this. And that's it, my friends. That's it. That's all. Hey, let's try a reaction. Let's try a question that involves making a diazo compound. So let me just go back to my slide. Just bear with me for a second here. I'll find them. Oh, where are they? Somewhere back here. Here. We were talking about diazonium ions and how you could make an azo dye. Well, there's a question that I have in here. Question 22.7. It says, identify the reactants that you would use to prepare this azo dye via an Azo Coupling reaction. Well, I mean, really, you're either going to have the diazonium, breaking this bond or breaking this bond. So if you break the bond in red, then you'd end up having your diazonium ion on this. So let me just draw it out for you. So you'd have your diazonium here, like this, and then you have a sulfonic acid here, and you have a sulfonic acid over here, okay? And then your nucleophile would be aniline, okay, like this, okay? So that would be, one way, and the other way would be if you broke the black bond, then this would be your quote-unquote nucleophile. So you'd have a sulfonic acid and a sulfonic acid over here. And then you'd have this as your electrophile. So you'd have, you'd have your diazonium ion over here. That doesn't look very good. Let's just write it like this. There we go. All right, so which scenario is best? There's one of these that's good and one of these that is not, okay? This or this. Which one is going to be the best way to set this up? Would you want to react with this diazonium ion or with this diazonium ion? Well, let's go back in our notes and see if we can make some sense of this. What it said was the diazonium salt is going to serve as an electrophile. So it's going to be attacked by an activated aromatic ring. Well, if we go back here and you compare, so let me circle the two rings, that would be the nucleophile. What's going to be a more activated ring? This one in the yellow circle or this one in the green circle? Which one of these would be more activated? The one with the electron donating group, the one in the yellow circle, or the one with the electron withdrawing groups? which one is more activated? Could anybody tell me which one of these is more activated? When we talked about activating groups, deactivating groups in chapter 18. Which one of them is going to make a better nucleophile? Well, I'd say it's the one in the yellow circle, because this one has an electron donating group on it, and this one has 2 electron withdrawing groups on it. So since these things are withdrawing electron density away, just pulling it away like crazy, this is not going to be a very good nucleophile. Okay, this is going to be a crummy nucleophile, whereas aniline is going to be a great nucleophile. So if we draw out the Diazonium ion like this, okay, like that, I mean, this is definitely going to do a nucleophilic attack like that. Okay, so that would be the best strategy. So if we just move down here, the way you'd want to do this is to do some Sandmaire chemistry. I'm just going to rewrite this compound as the amine. So I'd want to have the amine here. I have my sulfonic acid here, my sulfonic acid here. And then I'm going to diazotize, so use sodium nitrite and HCl. And then I would treat that with my aniline. So aniline like this. And that is going to give me my product. That's the best way to build this compound. The whole part about nitrogen heterocycles is something we skip. I'm not going to ask you any questions about pyrrole and pyrimidine. However, it's a very short section, so I would say it's not necessarily a skip. I'd say it's more of an FYI. You know, if you want to take the time to read through that, I think it's a good thing. And the reason why is because heterocycles show up in so many drugs that it's a good idea to have some knowledge of heterocycles. For example, you know, you see that we have a pyridine in here. This thing is called a benzimidazole here, and this portion is called an imidazole. So those are some heterocycles. This molecule is called piperazine, or this portion is called piperazine in here, and then we have another big heterocycle over here in Viagra and Nexium. So you can find all kinds of heterocycles, and but really, I'm not going to be asking you about any substitution on any heterocycles, so don't stress about that. And then the same thing about this section on spectroscopy of amines. I think I might have one question about that in the homework, but I don't think there's any on the quiz, but there could be, because this is covered in detail in Chemistry 3101 when we do chapter 14, the IR chapter and the MS chapter, and then the NMR chapter, and it's also covered in the Organic 1 and the Organic 2 labs. So just remember that you have broad stretching for a primary amine and a secondary amine, and that a secondary amine only gives you one broad signal. Well, that's not a very good signal, is it? One broad signal like this, whereas a secondary amine gives you one, whereas a primary amine gives you 2. So it kind of looks like this, right? And they are for asymmetric and symmetric stretching. Again, that's something that we cover in detail in Organic Chemistry 1. Of course, a tertiary will not give you a nitrogen-hydrogen stretching signal, so nothing to worry about there. Then we talk about nitrogen-hydrogen protons. Just like an oxygen-hydrogen proton found in an alcohol or a carboxylic acid, or sorry, an alcohol, not a carboxylic acid, but they can be found in a wide variety or in a big part of the NMR spectrum, anywhere from 0.5 to 5 parts per million. And all kinds of things can affect the chemical shift of the hydrogen attached to a nitrogen, like concentration. Anyhow, and we also talk about how a hydrogen attached to a nitrogen gives you a broad signal. It has no splitting. So we cover that in Organic Chemistry 1. Then we talk about the effect of being next to nitrogen, which is an electron withdrawing atom. It's got an electronegativity of around 3. So we cover that again in Organic Chemistry 1. Then we talk about alpha fragmentation. This is again covered in chapter 14 of Organic Chemistry 1, alpha fragmentation. And there you go. So let's just take a look at all the different reactions we covered, because there were a few. This one is a review. This one's from chapter 7. Okay, this is a chapter 7 reaction from Organic Chemistry 1. Just an SN2 with a cyanide to make a nitrile, which can be reduced with lithium aluminum hydride. Then,